In this problem, we want to determine several parameters associated with an NPN transistor. Important concepts include the NPN transistor, the Shockley equation, the fact that emitter current equals collector plus base currents, alpha, which is the collector to emitter current ratio, and beta, which is the collector to base current ratio. Let's see what we have in the problem statement. We have an NPN transistor, which is operating at room temperature, and it has various characteristics that are listed here. We are looking for two voltages, two currents, and a ratio alpha. We are to assume that the transistor is operating at room temperature. Now the NPN transistor looks like this. It has three terminals: the collector, the base, and the emitter. And it has associated voltages, the base to emitter voltage, the base to current voltage, which I'll go ahead and add right here. It has the base current, the collector current, and alpha is a special parameter of the transistor. It is the ratio of the collector current to the emitter current. Now let's see how some of these other transistor characteristics relate. Beta is the ratio of the collector current to the base current. This is a type of current gain, and for this transistor the value of beta is 100. The collector to emitter voltage is 10 volts, and we also know that the emitter current is 10 milliamps. Now let's look at the Shockley equation, which describes the transistor emitter current in terms of a number of different parameters. First is I sub ES, then we multiply this by E raised to the base emitter voltage divided by the thermal voltage, VT, and then we subtract 1. Now the emitter current is known because that's specified in the problem statement, as is I sub ES. The thermal voltage is specified as 26 millivolts at room temperature, so we can solve that equation for VBE. And that's the first voltage that we were looking for. The second voltage is the base to collector voltage, and we can find this from Kirchhoff's voltage law. If we start at the emitter terminal and work our way around, we would first encounter minus VBE, and then plus VBC, plus VCE, and we're back at the emitter terminal, so we set that result equal to 0. Now VCE is known, as is VBE. We just found that from solving the Shockley equation, and we can then find the base to collector voltage. Alright, that would be the second thing we're looking for. Now we have the base current, the collector current, and alpha. Now by KCL, we see that the sum of the collector and base currents is equal to the emitter current. Now we know that the emitter current is 10 milliamps. We know that the collector and base currents are related by this ratio, which is equal to 100. We could then say that the base current is the collector current divided by beta. With a substitution right there, we now have a single equation in a single unknown, and we could solve that for the collector current IC. Alpha is known once we know the collector current. Alright, let's proceed to the detailed solution. First, let's work on finding the base to emitter voltage. We'll begin with the Shockley equation. I sub E, or the emitter current, is known to be 10 milliamps. I sub ES is known, as is V sub T. So let's solve for this voltage VBE. Now this exponential is normally much greater than 1, and it's common practice to ignore the -1 in the Shockley equation. And we can do this without really losing any significant accuracy. So we work on isolating VBE. Here we can take the natural log of both sides, and that will undo the exponential. Put VT on the other side. And at this point we can start putting in numerical values. All three of these are specified by the problem statement. This evaluates to 10 to the 11th power, so natural log of that is 25.33. And from this we find that VBE is 658.5 millivolts, just under 0.7 volts. And that value is actually typical for an NPN transistor. We can apply Kirchhoff's voltage law now to find VBC, or the base to collector voltage. Starting at the emitter terminal, I'll work my way around clockwise. We have minus VBE plus VBC plus VCE. We're back at our starting point. Set the result equal to 0. We're trying to find VBC, so I'll put everything else on the other side of the equation. So we had a value for VBE, and the collector to emitter voltage is 10 volts from the problem statement. And VBC then is minus 9.341 volts. All right, let's start working on the currents. We need both IC and IB. These are related together by the parameter beta. Also, by Kirchhoff's current law, we recognize that the sum of these two currents is equal to a known value for us, which is the emitter current. All right. Let's recall then that the value beta is the collector current divided by the base current. Now we're looking for a collector current, and collector current can also be related back to the emitter current by the factor alpha. Alpha is also one of the things we are looking for in this problem. So let me first take the top current gain here. I'll express I sub B, the base current, in terms of the collector current. Go ahead and make that substitution. And now we have the opportunity to solve for the collector current. So we can isolate I sub C. And we have 10 milliamps divided by 1 plus 1 over 100. And the denominator is 1.01. That tells us that the collector current is always going to be slightly less than the emitter current. Again, it's the base current that makes up the difference there. So we find that the collector current is 9.901 milliamps. And I think we've now got enough information to find the value alpha. And actually we needed to find the base current first, so that was a pretty easy solution once we know the collector current. In terms of alpha, we would have the collector current divided by the emitter current, and alpha is 0.9901. Again, the maximum value for alpha would be 1. All right, let's review the problem-solving approach we followed. First, we recalled the Shockley equation for the emitter current and then solved for the base emitter voltage VBE. We then applied KVL to solve for the base collector voltage VBC. We then applied KCL to express the emitter current in terms of the base and collector currents. We recalled the definition of beta and wrote the collector current in terms of the emitter current and beta and solved. Then we solved for the base current knowing that beta and the collector current are related. And finally, we recalled the definition of alpha and solved for its value.